Chapter 5 Permutation Groups. Let A be a non-empty set. A permutation on the set A is just a bijection from A to A. It is a one-to-one and one-to function from A to A. The permutation group on the set A consists of all permutations under the operation composition of functions. It is a group under this operation, and it is called symmetric group, the symmetric group on the set A. We'll be studying here the case when A is a finite set. In that case, we can restrict ourselves to this case when A is the set of the numbers from 1 to n. These are just indexes. Or we can say that the nature of the elements of A is not important. That's why we can label them first, second, and so on, nth element of the set A. Here, a permutation when the set is finite will be given explicitly as a table. For example, if A is the set from 1 to 4, we can specify the bijection alpha by writing all the values of alpha on the elements of A. Alpha of 1 is 2, alpha of 2 is 3, alpha of 3 is 1, and alpha of 4 is 4. For example, this one bijection. A more convenient way of writing this alpha is this table. In the first row we write all elements of A. In the second row, under each element we write its image under alpha. So this means that under alpha 1 goes to 2, alpha of 2 is 3, alpha of 3 is 1, and alpha of 4 is 4. Composition of permutation, so expressed in array notation, is carried out from right to left. For example, we can compute gamma sigma if sigma and gamma are this by applying first alpha, first sigma, and then to the result applying gamma, because this is how composition of function works. The number, we want to find what is the image of 1 under this composition. First we find sigma of 1. Sigma of 1 is 2, and then what is gamma of 2? Gamma of 2 is 4. So the composition sends 1 to 4. What is gamma sigma of 2? First 2 goes to 4, and then 4 goes back to 2. So the composition sends 2 to 2. Gamma sigma of 3 is 3 goes to 3, and then 3 goes to 1, so 3 goes to 1. Gamma sigma 4. Sigma of 4 is 5, gamma of 5 is 3. So 4 goes to 3 under the composition. And finally, 5 goes to 1, 1 goes to 5, 5 goes to 5. This way we find composition of permutations. Composition of permutations is always also a permutation. The symmetric group S3 consists of the set of all permutations from the set 1, 2, 3 to itself. And the operation is composition. How many different tables of bijections can we write? The first row is always 1, 2, 3, and in the second row we must have all the numbers 1, 2, 3, but in different orders. There are 3 factorial, 6 possible orders of the second row. So we have 6 possible permutations in S3. So S3 is a group of order 6. Similarly, Sn is the set of all permutations on the set from 1 to n. How many tables can we write for a permutation from Sn? The second row is a permutation of the numbers from 1 to n, and we can have n factorial different permutations. So Sn is a group of order n. Cycle notation. Cycle notation has a theoretical advantage in that certain important properties of permutations can be readily determined when cycle notation is used. As an illustration of cycle notation, we consider this permutation in the symmetric group S6. We can represent alpha this way. 1 goes to 2 and then 2 goes to 1. So 1 goes to 2 and alpha. We write this arrow and label it with alpha. And 2 goes to 1 and alpha. So I have this cycle. And 3 to 4, 4 to 6, 6 to 3. 3 to 4, 4 to 6, 6 to 3. The second cycle. And finally, 5 goes to itself. We have a cycle of length 2, a cycle of length 3, and a cycle of length 1. So alpha can be written in a line like this, instead of drawing such diagram. It takes a lot of space on the page. We encode this 2 cycle by writing 1 and then 2 in parentheses. And the 3 cycle is encoded this way. And the 1 cycle is this. So if we see this 3 cycle, it means 3 goes to 4, 4 goes to 6, and the last number goes to the first number. In cycle of length 1, the number goes to itself. An expression of this form is called a cycle of length n. Here all the numbers must be different. A multiplication of cycles can be introduced by thinking that a cycle is a permutation that fixes any symbol not appearing in the cycle. Thus, a cycle 4-6 can be thought as representing this permutation. Any number that is different from 4 and 6 goes to itself. 4 goes to 6, 6 goes to 4, and 5 also goes to itself. In this way, we can multiply cycles by thinking of them as permutations given in array form. Consider the following example from the symmetric group S8. Let alpha be this product. These are disjoint cycles, and beta be this product. Show that alpha beta is equal to this. How is show this? What is alpha beta of 1? First beta of 1 is 2, and then alpha of 2 is 7. So alpha beta of 1 is 7. We open a cycle, write 1, and after that 7. After 7, we have to write the image of 7 on the alpha beta. 7 goes to 1 on the beta, and 1 goes to 3 on the alpha. So alpha beta sends 7 to 3. 3 goes to 7, and then 7 goes to 2. So on the alpha beta, 3 goes to 2. 2 goes to 3 on the beta, and then 3 on the alpha goes to 1. So 2 goes to 1 on the alpha beta, which means that this cycle closes. Then we open a new cycle and select a number that does not appear here in the first cycle. The smallest such number is 4. Then the image of 4 on the alpha beta is 4 goes to 8, and then 8 is fixed. Then the image of 8 on the alpha beta, 8 goes to 6, and then 6 goes to 4. So this cycle closes. Then we look for a number that is not written in this cycle and not in this cycle. The smallest such number is 5. Open a cycle, write 5. The image of 5 on the alpha beta is what? 5 goes to itself on the beta, and then 5 goes to 6 on the alpha. So alpha beta sends 5 to 6, write 6 here after 5. Then what is alpha beta of 6? 6 goes to 4 on the beta, and then 4 goes to 5 on the alpha. So alpha beta sends let's see again. Beta sends 5 to 5, and alpha sends 5 to 6. So 5 goes to 6, and then 6 goes to 4, and 4 goes to 5 on the beta. So 6 goes to 5. So this cycle closes. And now all numbers from 1 to 8 are already written. This means that we have finished. Alpha beta is written as a product of disjoint cycles. I leave this as an example for you to find alpha beta, write alpha beta as a product of disjoint cycles. the identity permutations has all numbers fixed. So in any cycle of length 1 is the identity permutation. So in the cycle decomposition of epsilon, we have one cycles only, and we can omit all of them except for one. So epsilon can be written this way or this way, or you can write all of them, but they are not needed. The one cycles, each of them is equal to epsilon. Disjoint cycle form is one in which the different cycles have no number in common. So two cycles are disjoint if no number of the first cycle appears in the second cycle. This theorem is true. Every permutation alpha can be written as a product of disjoint cycles. We already saw how this can be done. And it can be proved easily that if alpha and beta are disjoint cycles, then alpha beta is equal to beta alpha. That is, disjoint cycles commute. If cycles are not disjoint, they usually they don't commute. Theorem: the order of a permutation of a finite set when that permutation is written in disjoint cycle form, the order of the permutation is the least common multiple of the lengths of the cycles. Example: if we have a product of disjoint 2 cycle and 3 cycle, then the order of the product will be the least common multiple of 2 and 3, that is 6. A 2 cycle is called a transposition. Any transposition has this form, AB, where A and B are two different numbers. So a 2 cycle transpose A and B. That's why the 2 cycle is called transposition. Theorem: any permutation of Sn is a product of 2 cycles. So if it is a 2 cycle or a product of 2 cycles. A 3 cycle can be written as a product of 2 cycles this way. You write 2 disjoint 2 cycles, write I1. These are not disjoint. I1 appears in both. So it is not a requirement for the 2 cycles to be disjoint. They are not necessarily disjoint. Here they are not disjoint for sure. I1 appears in both. And you write I3, I2. I2, I3 here, we write them in reverse order. You can check that these permutations are the same. For example, the right-hand side sends I1 to I2 and then I2 to I3. So I1 goes to I3, I1 to I2, I1 goes to I2 and then I2 is fixed. And the left-hand side does the same. I1 goes to I2. The right-hand side sends I2 to I1 and then I1 to I3. So I2 goes to I3. And the left-hand side sends I2 to I3. And this any four cycle can be written as a product of three transpositions this way. You write I1, I1, I1 everywhere, and then I2, I3, I4 is the second end. These are the second entries but you write them in reverse order. I2, I3, I4. And similar rule applies for a 4 cycle, for a 6 cycle, and so on. This is a technical lemma given without proof. The proof is given in the book. If the identity permutation is written as a product of transpositions, then the number of transpositions is even. Using this lemma, one can prove that if a permutation can be written as a product of even number of transpositions, then any representation of that permutation must have even number of transpositions. And if a permutation can be written as a product of odd number of transpositions, then any representation of that permutation as a product of transpositions must have odd number of transpositions. And this allows us to give this definition. A permutation is called even permutation if it can be written as a product of even number of transpositions. Otherwise, it is called odd. Theorem: the set of all even permutations of the symmetric group Sn is a subgroup of Sn. How we prove this? By using the finite subgroup test. It is enough to prove that the set of even permutations is closed under composition, which is easy to prove. This subgroup of all even permutations of Sn is called alternating group of degree n, and it is denoted with A sub n. It has n factorial divided by 2 elements. That is half of the permutations of Sn. Exactly half of the permutations of Sn are even, the other half are odd.